There is a global race happening over a metal you have never once thought about, and China just pulled ahead by a margin that should worry every copper-dependent economy on the planet. China's breakthrough just replaced copper, and it changes how power, vehicles, and aircraft get built. A new carbon nanotube fiber out of the Shenyang National Laboratory now conducts 86% of what copper conducts, at 1/6 the weight. You heard that right, 86%. Roughly the difference between a compact car and a motorcycle on the same scale. And that is just the beginning. Because the real story is not the lab result. It is who moves first to industrialize it. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you will understand exactly why the world's biggest manufacturers are already paying attention. Copper has run the show since the telegraph. That reign has a shelf life now. Copper did not win its place in the modern world by accident. It won by being nearly perfect at the one job that matters most in electricity, letting electrons move with almost no resistance. Only silver conducts better, and silver costs roughly 90 times more per pound, which is the difference between wiring a house and wiring a jewelry box. Copper is also soft enough to draw into hair-thin strands without cracking, and stable enough to sit inside a wall for 80 years without corroding into failure. That combination is why it ended up everywhere. Engineers love copper because it behaves predictably under heat, load, and repeated bending, which means fewer failures in the field and fewer redesigns on the drawing board. Manufacturers love copper because the entire global supply chain, mining, smelting, wire drawing, insulation, has been optimized for more than a century, so every factory on Earth already knows how to work with it. Governments love copper because it is recyclable almost indefinitely without losing performance, letting nations treat old wiring as a domestic mine rather than a landfill problem. Here is the part most people never stop to consider. The wiring in your walls right now, the motor in your refrigerator, the transformer at the end of your street. All of it exists because one metal happened to be abundant, workable, and electrically generous all at once. Picture a spool of copper wire, the width of a garden hose. Uncoiled, a single residential spool can stretch nearly the length of 2 football fields, carrying current the entire way without meaningfully heating up or degrading. Every electric motor ever built, from the first 19th century prototypes to today's electric vehicles, was designed around copper's properties, not despite them. So why didn't anyone replace it sooner? Because nothing else came close. Aluminum conducts respectably, but corrodes at connections and expands under heat in ways that loosen joints. Silver works but bankrupts anyone who tries to use it at scale. For a century and a half, there was copper, and then there was everything else, several tiers below. That is not an accident of history. That is copper earning its throne through sheer material logic, cheap enough to mine at scale, soft enough to shape, stable enough to trust with your life inside a wall. And that trust is exactly why what comes next matters so much. Because brilliance built on one irreplaceable ingredient carries a hidden cost, and that cost has been quietly accumulating for decades, waiting for someone to finally add it up. Underneath copper's century and a half of dominance sits a structural vulnerability that has nothing to do with engineering and everything to do with geology. This is not about a metal running low. It is about a metal becoming steadily harder, slower, and more expensive to pull out of the ground. At the exact moment, the world needs dramatically more of it. Average copper ore grades have fallen roughly 40% since 1991, meaning mining companies now have to dig through nearly twice as much rock to get the same amount of usable metal, the equivalent of doubling the size of a quarry just to fill the same truck. At the same time, the International Energy Agency projects a 30% global copper supply shortfall by the year 2035. A gap wide enough to leave roughly 1 out of every 3 planned electric vehicles, data centers, or grid upgrades without the copper they were designed around. New mine discoveries have nearly collapsed, with only 14 major copper deposits found in the past decade, compared with 225 in the 23 years before that. A fall-off steep enough to make new supply feel almost accidental rather than planned. And a new mine, once discovered, takes an average of 17 years to reach production, roughly the time it takes a newborn to become old enough to drive. That lag means today's shortage was locked in years before anyone started worrying about it publicly. The consequence shows up long before any mine actually runs dry. Copper demand for electric vehicles alone is projected to climb from roughly 396,000 tons in 2023 to 2.6 million tons by 2035. A jump so steep that automakers are already redesigning motors just to use less of it per car. Here is the part most people get wrong. This was never a story about running out of copper entirely. It is a story about copper becoming a choke point, a single material bottleneck sitting underneath electric vehicles, renewable grids, and artificial intelligence infrastructure all at once, all competing for the same shrinking margin of supply. Which raises an obvious question nobody in the copper industry particularly wants to answer out loud. What happens when the world's most essential conductors simply cannot be mined fast enough to meet demand? In 2024, a research team on the other side of that question began answering it with data that was harder to dismiss than anything the field had seen before. The team that finally cracked this problem worked out of the Shenyang National Laboratory for Materials Science, part of the Chinese Academy of Sciences Institute of Metal Research. The same institution with a decades-long track record in advanced fibers and alloys. The core idea sounds almost too simple once you hear it. Take carbon nanotubes, hollow cylinders of carbon atoms just a few nanometers wide, thousands of times thinner than a human hair, and spin enormous bundles of them into a single continuous fiber, the way cotton gets spun into thread. Scientists have tried this for over 2 decades, and nearly every earlier attempt failed for the same reason. Individual nanotubes conduct electricity brilliantly on their own, but bundling millions of them together introduces tiny gaps and misalignments, like a rope woven from threads that never quite touch each other end to end. Electrons hit those gaps and scatter, and all that promised conductivity leaks away in the transition. Here is the part that changes everything. The Shenyang team refined a technique called dry jet wet spinning, tightening the alignment of the nanotubes so more of them run parallel, touching along their length rather than crossing at odd angles. Picture combing out a tangled head of hair until every strand runs the same direction. The comb does not change a single strand. It just gets them all pointing the same way. And suddenly, the whole thing behaves as one unit instead of thousands of loose ends. That alignment is what let the resulting fiber reach 86% of copper's electrical conductivity, a number no comparable carbon fiber had reached before, while also hitting a tensile strength of 1.65 gigapascals, strong enough to support roughly 160 times its own weight without snapping. That single figure, 86%, is the kind of number that sounds modest until you remember copper had a 150-year head start and no serious competitor ever got within striking distance before. Earlier carbon fiber attempts topped out closer to 40 or 50% of copper's conductivity, which is why they stayed lab curiosities instead of becoming wire. This fiber cleared that ceiling by a margin wide enough to matter commercially, not just academically. The question was no longer whether nanotubes could theoretically rival copper. Real fibers, spun on real equipment, were now proving it in practice. And proving it once in a single controlled test is very different from proving it holds up under years of real-world stress. Start with the honest number, not the flattering one. 86%. Conductivity means this fiber still loses to solid copper on a straight apples-to-apples electrical comparison. For the same cross-section, copper still moves more current with less resistance, full stop. But here is what that number actually means in practice. Almost nothing in the real world is a straight apples-to-apples comparison, because wires are never evaluated on conductivity alone, and they are evaluated on conductivity per unit of weight, and that is where this fiber stops competing with copper and starts beating it outright. Copper weighs roughly 8.9 grams per cubic centimeter. This carbon nanotube fiber weighs about 1/6 of that, closer to 1.4 grams per cubic centimeter, similar to the density difference between a solid steel dumbbell and a foam pool float of the same size. Match them for equal weight instead of equal size, and the nanotube fiber can carry more current than copper does, not less. That is the unexpected advantage most coverage misses entirely. This is not a story about matching copper. It is a story about beating it, once weight enters the equation. Here is the detail that puts everything into perspective. A satellite designer or an aircraft engineer does not care whether a wire technically loses on paper. They care what a mile of usable wire weighs once it is installed. And on that measure, copper has just lost its long-standing advantage. The fiber also survived over 5,000 bending cycles without measurable conductivity loss. A durability profile copper wire cannot match once repeated flexing starts, causing microscopic fatigue cracks. That single property already makes it the front runner today for one very specific, unglamorous application: wiring inside aircraft and drones, where every gram removed from the wiring harness translates directly into fuel savings or extended flight time. Consider what that weight savings compounds into across an entire aircraft. A single long-haul jet can carry several miles of copper wiring bundled through its fuselage, all of it dead weight the moment the engines are running, none of it contributing lift. Cut that wiring's weight by even a third using a nanotube alternative, and the fuel savings over an aircraft's operating life start to resemble the payload of an extra passenger or two, carried for free, every single flight. The question was no longer whether the fiber worked. The question was how quickly it could move from laboratory spools to wiring harnesses people actually fly on. The first serious field validation did not happen in a showroom. It happened in the unglamorous world of aerospace prototyping, where Chinese aviation researchers began testing nanotube fiber wiring harnesses in unmanned aircraft platforms starting in 2024. Tracking performance across repeated flight cycles rather than a single lab measurement. The field matched the forecast. Conductivity held near the 86% mark across dozens of test flights, and the fibers showed no measurable degradation after the kind of vibration and temperature swings a wire experiences at altitude. Conditions far harsher than the 5,000 bending cycles tested in the original laboratory study. Field validation matters more than lab results in this industry because aerospace wiring cannot fail quietly. A wire that performs perfectly on a bench but degrades after 6 months of real vibration is not a solution, it is a future incident report. One detail lowered the barrier to adoption more than any performance number. The fiber can be produced using a modified version of existing dry jet wet spinning equipment, meaning manufacturers did not need to build entirely new factories from scratch, only retrofit lines already built for advanced fiber production, the difference between renovating a kitchen and demolishing a house to build a new one. As one materials engineer involved in aerospace testing put it, the hardest part was never proving the physics. It was proving you could make kilometers of it without the quality falling apart. Public research data on the fiber's testing methodology and conductivity measurements has been archived through the peer-reviewed science publication process, giving independent labs elsewhere a documented baseline to try to replicate, rather than taking the results on faith. That kind of open documentation is what separates a genuine engineering breakthrough from a press release with good marketing. If a fiber lighter than copper and nearly as conductive surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one application where weight mattered more than the small conductivity gap: aircraft wiring. Then it spread outward from there into drone manufacturing and early-stage satellite component testing. Each new application borrowed credibility from the last. The way a first successful bridge crossing makes every engineer more willing to trust the material for the next one and the one after that. The claim now had receipts. More than 40 international patent families now cite advanced carbon nanotube fiber conductor technology, filed across China, the United States, Japan, and the European Union. These are not academic citations. These are legal and financial commitments, the kind companies only make when they expect a return within a specific window of years, not decades. Jiangsu Nanotechnology, one of China's largest nanotube producers, now holds more than 40 of its own domestic and international patents covering nanotube production processes, positioning itself to supply raw material at industrial scale the moment demand accelerates. Toray Industries, the Japanese fiber giant, best known for aerospace-grade carbon fiber, has been expanding its conductive nanotube dispersion capacity specifically to serve electric vehicle battery and electronics manufacturers. In the United States, the startup Dexmat has commercialized its own nanotube fiber product under the brand name Galvorn, targeting exactly the same aerospace and electronics wiring niche this Chinese breakthrough now competes for directly. Meanwhile, aerospace-grade nanotube composite materials already command prices 3 to 5 times higher than standard industrial grades, and analysts project that segment growing at a compound rate near 17.5% annually through 2035. A growth curve steep enough that the market's total value is expected to roughly quadruple within a decade. Regulatory pressure is accelerating the shift too. Aviation efficiency mandates in the European Union and China alike are pushing manufacturers toward any material that trims aircraft weight without compromising safety certification, and nanotube wiring qualifies on both counts. Here is what most people get wrong about this competition. It was never going to be won by whoever invented the best fiber in a lab. It will be won by whoever can manufacture it consistently, at scale, cheaper than the last competitor. In any market where a lighter, nearly as conductive wire cuts fuel and material costs simultaneously, an 86% conductivity trade-off is not a curiosity. It is a competitive pressure no serious aerospace or electric vehicle manufacturer can afford to ignore. The underlying research remains published and openly accessible through science, letting any lab on Earth verify the numbers rather than take a company's word for it. That transparency is precisely what turned a single Chinese laboratory result into a global scramble, instead of a claim other manufacturers simply doubted from the sidelines. Every competitor, now racing to catch up, is racing against a documented, reproducible baseline, not a rumor. Scale this technology up to a meaningful fraction of global wiring demand, and the numbers get genuinely large. Even capturing just the aerospace and drone wiring segment, a small slice of copper's total use would mean displacing tens of thousands of tons of copper annually, roughly equivalent to the weight of several aircraft carriers worth of metal simply no longer needing to be mined, smelted, and shipped every year. Extend that same substitution into electric vehicle wiring harnesses, where automakers are already fighting for every pound of weight savings, and the volume of displaced copper could climb into the hundreds of thousands of tons within a decade. There is a secondary benefit too, one that rarely makes the headlines. Every ton of copper mining avoided also avoids the water-intensive extraction process that has been straining drought-affected mining regions like Chile, where copper production already competes directly with agricultural and municipal water use. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. Production costs remain 3 to 5 times higher than standard carbon fiber grades, a gap that has to close substantially before nanotube wiring reaches ordinary consumer electronics. Manufacturing consistency at kilometer-scale lengths remains unproven outside pilot lines, and aerospace certification processes for any new wiring material typically take 3 to 5 years before regulators sign off. The fiber's moisture sensitivity, identified in related nanotube fiber research, means humid environments can degrade performance over time unless the wiring is properly sheathed, an added manufacturing step and an added cost. And copper's supply chain, built over a century and a half, still has enormous inertia. Switching an entire industry's wiring standard is not a single decision, but thousands of individual purchasing decisions made independently across suppliers who have trusted copper for their entire careers. Here is the part that puts the whole picture in perspective. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the copper shortage demands is a different question entirely. The story of a carbon fiber quietly rivaling copper is ultimately the story of what human civilization can build and where it can build it. For most of industrial history, access to reliable electrical infrastructure has tracked almost exactly with access to cheap copper, which meant nations sitting far from major copper deposits or lacking the capital to import it paid a permanent electrification tax that wealthier, copper-rich regions never had to think about. A lighter, less resource-concentrated conductor changes that math, at least at the margins. Remote grid extensions, offshore energy infrastructure, and aerospace-adjacent manufacturing in countries without their own copper mines all become slightly less dependent on a supply chain concentrated in a handful of nations. What is genuinely new here, not incrementally better, but categorically different, is a conductor whose performance per weight can exceed copper's, produced through a manufacturing process adaptable to existing industrial fiber lines, rather than requiring an entirely new global supply chain built from scratch. That is not a minor improvement. It is a different category of solution to a shortage that mining alone cannot fix in time. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the copper shortage demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. And scale is exactly why this matters more than one laboratory paper. A conductor breakthrough compounds the way copper's own advantages compounded for a century and a half. Every wiring harness redesigned, every kilometer of fiber manufactured cheaper than the last, makes the next application easier to justify. If a lighter alternative to copper raises the obvious next question, what happens when engineers apply that same weight versus strength thinking to the metal holding buildings and bridges together? That story is worth understanding too, and it is the subject of our next video. China's new steel is 3 times stronger, yet uses 30% less metal. The link is in the description. If this changed how you think about the metal running through your walls, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. If a nanotube wire beats copper on weight, but still trails it slightly on raw conductivity, should aerospace switch now, or wait for the numbers to close completely first?